So, why are areas under curves important? It's very easy to understand that through an example. Imagine you're driving a car at a constant velocity of, say, 35 miles per hour. If that's constant, and that's your velocity, we can say that the velocity function v of t equals 35 as a constant. And if you graph that, then y equals 35. That is a horizontal line there. And if your intention is to drive that way for 2 hours, let's say, so between t equals 0 and t equals 2 as an example, then we all know that the distance traveled is 35 times 2, which is 70 miles. So we know that. But we also notice that this is the area of this square right here, or this rectangle, right? It's not a square. Looks like one, but it isn't. So it's base 2 and height 35. So the area under velocity curve corresponds to the distance traveled in that interval of time. Remember that when we studied derivatives, we saw that the derivative of the distance, right, of the position function was velocity. Now we're saying that the area under velocity, right, goes back to the original function, to the position function. So we're like undoing what the derivative did already. Let's see what happens here in this example when the velocity function is a little bit more complicated than just a constant function. So now v equals t squared is a parabola. V of t equals t squared. That is, the graph of this is a parabola. So this is going to be a concave upward parabola like this. A lot more difficult to calculate the area under this thing. So what we do is we approximate it. How are we going to do that? Let's see. On item A, we're going to divide the interval 0, 8, which is our interval of time, in two subintervals, 0, 4 and 4, 8. So this is going to be our 0, this is going to be our 4, this is going to be our 8, our parabola, and then I'm ignoring scale just to make it easy. It's going to be like this. This here, right, going to be the two areas I want to add, approximate to add. So the first area, I'll approximate the height here by the height at the middle. So at 2, I decide that because I was told to do that, using the midpoint 2. So what is v of 2? That will be 2 squared, which is 4. So this is 4. So at that point, I'll make a rectangle of height 4 and base 4. So this first area is 4 times 4, which is 16. The second area, I'll use the midpoint between 4 and 8, which is 6. V of 6 for me is 6 squared, which is 36. So the height will be right here at 36. And then I'll use this rectangle right here as an approximation for the area under the blue curve. So this blue area is base times height, so 4 is the base, right? 8 to 4, 8 minus 4, times the height, 36, right? And whatever that is, I have my calculator just to make sure that I don't make a mistake. That would be 144. Makes sense. It's 12 squared, right? If I move the 3 over, I get a 12 times 12. So these are the two areas. So that means that I can approximate the area under that curve by 16 plus 144, right? Which is 160. So if that's my velocity, I can approximate the distance traveled in this interval by 160 miles, right? That's a fair approximation using those two subintervals. I can make my approximation better if I use more subintervals. So in this example, I could do B, right? from 0 to 8, I'm dividing into 4 subintervals now with the same length. And then on each of those, I'm calculating the height by v of the midpoint. So the middle here is 1, so v of 1 is 1 squared, which is 1. So here I'll do height 1. Here v of 3 is 9, so here I'll do 9. Again, it's not to scale. That's the other length I'll use. And then here v of 5, right? So 25. Right here, and that's the height of my rectangle there. And then the last one would be v of 7, right, the midpoint, because I'm told to use the midpoint. 49, so that's 49 is that height. So I add these 4 areas together, and that's going to be an approximation for this area that I have here, right? The area under my curve from 0 to 8, right? An approximation for it. You can see in the previous picture, you can see that this red rectangle here, right? It misses part of the area here, but it also adds a part of the area that I don't want. So there's some sort of a balance there, and the same is going to happen on these. So this is a good approximation as well because of this. This is why I'm using the midpoint as well. I add some area that's not part of it, but I also forget to add some of the area that is part of it. So this kind of balances things out. So the actual approximation in this case will be, so on the first rectangle, 2 times 1, so 2. On the second one, note that the base is again 2, so 2 times 9, 18. On the third rectangle, base 2 times height 25, so 50. And on the fourth rectangle, base 2 times height 49, so 98. I'm right about this, I think, but if I'm incorrect, you can let me know. So adding everything, I believe I do get, so if I combine this with this, that's 100, with that 150, with that 168. 168 miles traveled. So that's another approximation. Note that they're very close to each other, the two approximations I have. This one's a little higher. And I also believe this one is better because I have more intervals. So the little errors when I draw, if I were to draw, right, the graph of the function, it's going to be a little bit of a challenge there to draw the graph after the rectangles. But the errors are smaller here. The errors are smaller. Each error is smaller. So I do believe this one better. I can repeat the reason for C, which asks to divide in 8 subintervals of equal length. So now I'm going to do 8 subintervals. 0, 1, 2, 3, 4, 5, 6, 7, and 8 are going to be the endpoints. And I'm going to calculate v of 0.5, v of 1.5, v of 2.5, and so on. So these are the basics of this, and this is why this is interesting. We get an approximation of distance traveled with the area under curve. This is pretty interesting, I think.